Ever find yourself looking at a simple number like 7 and thinking about all the different things it can represent, like 7 apples or 70 miles or even, $700? It's kind of amazing how one little digit can mean so much, right?
It really is, and that amazing flexibility all comes down to a concept called place value. It's essentially the idea that a digit's value is determined by, well, its place in a number.
So it's like each digit has a specific address, and that tells you its relative size.
Exactly. Think of it as a secret code embedded within each number, revealing the true magnitude of each digit.
That's a great analogy. And in this deep dive, we're going to decode this system. We'll be exploring place value in both whole numbers, those familiar everyday numbers, and also diving into decimals, which can sometimes feel a bit more mysterious.
And believe it or not, understanding this system is like unlocking a superpower for working with numbers. It really underpins almost everything we do with math, from basic arithmetic to more complex operations.
Okay, so let's start simple. What's happening when we look at a whole number, like, say, the number 352?
Well, in any whole number, the place value of each digit is determined by its position, starting from the rightmost digit. That very first position, the one on the far right, is called the ones place, or sometimes the units place.
So if I see a 2 in the ones place, I know that means I have two individual items, right?
Precisely. It's a direct representation of that quantity. Now, if we move one position to the left, we come to the tens place.
Ah, so here the digits are representing groups of 10, not just single units anymore.
Exactly. So if you have a 5 in the tens place, that doesn't mean 5 units. It actually represents 5 groups of 10.
Which would be 50. And if we move another step to the left,
That lands us in the hundreds place. So here each digit represents a group of 100.
I'm starting to see a pattern here. Each place we move to the left, the value of the digit gets 10 times bigger.
You got it. That's the beauty of our base 10 system. Each place value is 10 times greater than the one to its right. It's a beautifully consistent structure.
And I'm guessing this pattern continues as we move to even larger numbers.
Absolutely. After hundreds, we have thousands, then 10,000s, which is 10 groups of 1,000, and then 100,000s, which is 100 groups of 1,000, and then we get to the millions.
Wow, the numbers get big fast. But to be honest, when I see a really long number, it's easy to get lost in all those digits. Is there a way to make reading those easier?
Absolutely. That's where commas come in. They help us visually break down large numbers into manageable chunks. These groups of 3 digits are called periods.
Periods, like at the end of a sentence.
Not quite. In math, a period is just a group of 3 digits in a number. The first period, starting from the right, is the ones period, which includes the ones, tens, and hundreds places. Then we have the thousands period, the millions period, and so on.
Okay, that makes sense. So for example, if we had the number, let's say, 1,234,567, those commas are telling us where each period begins.
Exactly. And if we break down the place value of each digit in that number, we can see this system in action. The 7 in the ones place represents 7 units. The 6 in the tens place is 60. The 5 in the hundreds place is 500. Moving to the left of the comma, the 4 in the thousands place is 4,000. Then the 3 in the 10,000s place is 30,000. The 2 in the 100,000s place is 200,000. And finally, the 1 in the millions place represents a whopping 1 million.
So that little one all the way on the left carries a whole lot of weight.
It really does, and it perfectly demonstrates how the position of a digit drastically affects its overall contribution to a number's value.
Okay, we've got a good handle on whole numbers now, but what about numbers smaller than 1? How does place value work with decimals?
Decimals have their own translating system, and the key to understanding it is the decimal point. It acts as a clear separator between the whole number part and the fractional part of a number.
So it's like a boundary where whole numbers end and fractions begin.
Exactly. And just like with whole numbers, the digits to the right of the decimal point have place values that are determined by their position. But this time, instead of representing groups of 10 and hundreds and thousands, they represent fractions.
Fractions. So are we talking about pieces of a whole?
Precisely. The digits to the right of the decimal point represent fractions where the denominator, the bottom number of the fraction, is a power of 10.
Okay, I'm intrigued. Walk me through those place values after the decimal point.
All right, the first position to the right of the decimal is called the tenths place. A digit in this spot represents 1/10, or 1 part out of 10, which can also be written as 0.1.
So if I saw a 4 in the tenths place, that would mean 4/10.
You got it. Now, moving one more position to the right, we arrive at the hundredths place.
Hundredths. So we're getting even smaller now.
That's right. A digit in the hundredths place represents 1 part out of 100, which can also be written as 0.01.
So if I saw a 5 in the hundredths place, that would mean 500ths.
Precisely. And then, continuing our journey to the right, we get to the thousandths place.
Okay, I think I'm seeing the pattern again. As we move to the right of the decimal, each place value gets 10 times smaller.
Exactly. A tenth is 10 times larger than a hundredth, and a hundredth is 10 times larger than a thousandth.
All right, let's put this into practice. Say we have the decimal number 123.456. Can we break down the place value of each digit?
Absolutely. To the left of the decimal point, we have the whole number part. The 1 in the hundreds place, which is 100, the 2 in the tens place, which is 20, and the 3 in the ones place, representing 3. Now, to the right of the decimal point, we have the fractional part. The 4 in the tenths place, the 5 in the hundreds place, and finally the 6 in the thousandths place.
So we have 123 and then 4/10, 500ths, and 6,000ths.
Precisely. And it's that decimal point that neatly separates the whole number from those fractional parts, with the values decreasing systematically as we move to the right.
Okay, this place value stuff is pretty cool, but I have to ask, how does knowing all this help us actually do math?
It's more than just cool, it's essential. Place value is the backbone of all arithmetic operations. Take addition and subtraction, for example. When you're adding or subtracting, especially multi-digit numbers, you absolutely have to line up the digits according to their place value. You add ones to ones, tens to tens, hundreds to hundreds, and so on.
It's kind of like making sure you're comparing apples to apples, right?
Exactly. If you don't align the digits correctly, you're essentially trying to add or subtract quantities of different magnitudes, which just won't give you a meaningful answer.
And this is where those tricky concepts like carrying over, in addition, and borrowing and subtraction come into play, right?
Exactly. Let's say you're adding the numbers 345 and 287. When you add the ones column, 5 plus 7, you get 12. But that 1 and 12 actually represents a 10, so you carry over to the tens column because you can't stay in the ones place.
Ah, so it's like that 1 is being promoted to the next higher place value.
Exactly. And then in the tens column, you have 4 plus 8 plus the carried over 1, which equals 13. Again, that 1 and 13 represents 100, so it gets carried over to the hundreds column. All this carrying over and borrowing is based on the understanding that 10 of one place value unit is equal to 1 unit of the next higher place value.
That makes a lot of sense. So how does place value play into multiplication?
Well, place value makes multiplying by powers of 10, like 10, 100, or 1,000, super easy. You simply shift the digits to the left by the appropriate number of places. For example, if you multiply 123 by 10, you just move all the digits one position to the left, resulting in 12,230.
So multiplying by 10 essentially bumps every digit up to the next higher place value.
Precisely. And for more complex multiplications, you can use place value to break down the problem into smaller, more manageable steps.
Can you give an example of that?
Sure. Let's say you want to multiply 123 by 4. You can think of 123 as 100 plus 20 plus 3, based on its place values. Then you multiply each of those parts by 4. 100 times 4 is 400, 20 times 4 is 80, and 3 times 4 is 12. Finally, you just add those results together. 400 plus 80 plus 12, which equals 492.
That's a really clever way to break it down. And what about division? Does place value come in handy there too?
Absolutely. Especially in long division, you're constantly thinking about the place value of each digit in the number you're dividing, called the dividend. You figure out how many times the divisor goes into each part of the dividend, considering groups of hundreds, tens, or ones. And just like with multiplication, dividing by powers of 10 involves shifting digits, but this time you shift them to the right.
So it's the opposite movement for multiplication.
Precisely. Dividing by 10 moves each digit one place value to the right, essentially making it 10 times smaller.
So we've seen how place value is super important for doing calculations, but is it useful for anything else?
Oh, absolutely. Place value is also fundamental when we need to compare and order numbers. Let's say you have two whole numbers, like 567 and 582. To figure out which one is bigger, you start by looking at the leftmost digit, the one with the highest place value.
Well, in this case, both numbers have a 5 in the hundreds place.
Right. Since they're the same, we move one position to the right to the tens place. Here we have a 6 in 567 and an 8 in 582. Since 8 is greater than 6, we know that 582 is the larger number, regardless of what digit is in the ones place.
So the digits in those higher place values have a bigger impact on the overall size of the number. And what about when we're comparing numbers with decimals?
With decimals, the first step is to line up the decimal points. Then you compare the whole number parts, the digits to the left of the decimal point. If those are equal, you move to the right of the decimal and start comparing digits in the tenths place, then the hundredths place, and so on.
So it's still all about comparing digits in the same place value, even with decimals.
Precisely. And sometimes one decimal might have fewer digits after the decimal point than the other. In that case, you can imagine adding trailing zeros to the shorter decimal to make the comparison easier. For example, if you're comparing the 0.65 and 0.628, you can think of 0.65 as 0.650. Now, both numbers have the same number of digits after the decimal point, and you can see that 0.650, or 0.65, is larger than 0.628.
That's a helpful trick. And once we know how to compare numbers, we can easily arrange them in order, either from smallest to largest, which is called ascending order, or from largest to smallest, which is descending order.
Exactly, and whether you're comparing two numbers or a whole little of numbers, the same place value principles apply. You're always evaluating the contribution of each digit based on its position in the number.
Okay, we've covered a lot of ground here. Is there any other way we can think about place value to really solidify our understanding?
There is. We can use something called expanded form, which is basically a way of writing a number by showing the value of each digit separately based on its place value. For example, the expanded form of the whole number 123 would be 100 plus 20 plus 3.
So it's kind of like breaking down the number into its individual parts.
Exactly. And you can also write it like this: 1 times 100 plus 2 times 10 plus 3 times 1. This way, you can clearly see that the 1 is being multiplied by 100 because it's in the hundreds place. The 2 is multiplied by 10 because it's in the tens place, and the 3 is just itself because it's in the ones place.
I like that. It really emphasizes how each digit contributes to the overall value of the number. And I'm guessing we can do expanded form with decimals too.
Absolutely. For example, the expanded form of the decimal 12.34 would be 10 plus 2 plus 0.3 plus 0.04. This clearly separates the whole number part 10 plus 2 from the decimal part 0.3 plus 0.04.
And you could even write those decimals as fractions, right? Like 310 and 4100.
Exactly. Writing decimals in expanded form really highlights how closely connected they are to fractions. It helps you see that they're both just different ways of representing parts of a whole.
You know, it's amazing how well designed our number system is. It's so consistent and logical, and it's not just some abstract mathematical idea. We use it all the time in the real world.
It's true. Place value is everywhere, and we often use it without even realizing it. Think about money, for example. If you have $12.50, the 1 represents $10, the 2 represents $2, the 5 after the decimal represents 5/10 of a dollar, or 50 cents, and the 0 in the hundredths place signifies 0 cents.
Wow, it's hard to imagine how our financial system would even function without place value.
Exactly, and it's the same with measurements. If a piece of wood is 1.75 meters long, the 1 represents 1 whole meter, the 7 in the tenths place represents 7/10 of a meter, and the 5 in the hundredths place represents 5/100ths of a meter.
Or how about when we see those really big numbers in the news, like the population of a city being 8,321,456? It's place value that helps us make sense of those massive quantities.
Absolutely. Without understanding place value, those numbers would just be a jumbled mess of digits. But knowing that the 8 is in the millions place gives us an immediate sense of the scale we're dealing with. And did you know that place value even plays a huge role in technology, especially in computer programming?
Really? I wouldn't have guessed that.
While computers often work with binary, which is a base 2 system, the core idea of place value is still there. Each position in a binary number represents a power of 2 instead of a power of 10.
So the fundamental concept of place value is the same, even when the base changes.
Exactly. Understanding place value in our familiar base 10 system gives you a strong foundation for understanding other number systems used in various fields.
Okay, so to wrap things up, can we sum up the most important things to remember about place value?
Of course, the key takeaway is that place value is the value a digit has based purely on its position in a number. It's crucial to remember that this is different from the face value of a digit, which is just the digit itself. For example, in the number 789, the face value of the 8 is simply 8, but its place value is 80 because it's in the tens place.
And as we move from left to right in a number, the place value keeps getting smaller.
Exactly. Each place is 10 times smaller than the one to its left. It's a consistent pattern that makes our number system work so well.
So, to reiterate, understanding place value is crucial for accurate calculations, for understanding the size of numbers, and for interpreting the countless numbers we encounter in everyday life.
Precisely. It's like having the keys to a secret kingdom of numbers. And it's particularly important when we are performing addition and subtraction because it's only by aligning digits according to their place value and understanding how to regroup or carry over and borrow that we can ensure our calculations are correct.
We also can't forget about those decimals, remembering that relationship between tenths, hundredths, and thousandths, and how each is 10 times larger than the next smaller place value is critical for understanding those numbers smaller than 1.
You're absolutely right. And perhaps the most fundamental concept of all is that every single position in a number, whether it's to the left or the right of the decimal point, has its own unique place value.
Well, I think we've done a pretty thorough job of demystifying place value today.
I agree. Hopefully, our listeners now see that place value is not just some abstract concept, but a powerful tool for understanding the numbers that surround us. It makes math less intimidating and helps us see the order and logic inherent in our number system.
We encourage everyone to start paying attention to place value in their daily lives. You'll be surprised how often it pops up.
And on that note, here's a final thought for our listeners to ponder. Just imagine for a moment what our world would be like if we didn't have this consistent and logical system of place value. How would we handle money? How would we measure things accurately? How would we even count large numbers without a shared understanding of how a digit's position affects its value? It's truly mind-boggling to think about.
It really is. Place value is one of those fundamental concepts that we often take for granted, but it truly underpins so much of our modern world.